Okay, yeah, I got the notification. Okay. Good day, everyone. Our presentation for Milestone 3 Champions of the World is on the topic Practical Black Box Attack Against Machine Learning. Next slide. During this presentation, we'll cover a brief introduction of our topic. We'll discuss on our paper, the changes and the progress we've made, the difficulties we encountered, and how we managed to solve them. And finally, we'll wrap things up in a conclusion. Next slide. Our team is Team Antagonist and consists of myself, Ridi, and my teammate, Chua-Shin. So let's get into a brief introduction. Machine learning models such as deep neural networks, DNN, can be vulnerable to adversarial examples, that is, malicious input modified to yield erroneous model outputs while appearing unmodified to human observers. In the recent years, deep neural networks have achieved a considerable success in the field of computer vision. For example, image classification, face recognition, and self-driving. Nevertheless, there are still many concerns regarding the stability of neural networks. Most of the existing adversarial attacks can only fool a black box model with low success rate. To address this issue, we utilize an attack strategy which consists in training a local model to substitute for the target model, using inputs synthetically generated by an adversary and labeled by the target. Typically, an adversary crafts adversarial examples via a substitute model, which is a white box model, and then transfers them to the victim model, which is a black box model for attacking. Next slide, please. So as you can see on these slides, we provide the link to our paper and also a snapshot of our paper. Next slide. So now I'll summarize the content of our paper. So they introduce an attack based on a novel substitute training algorithm using synthetic data generation to craft adversarial example misclassified by black box DNN. Their work is a significant step towards relaxing strong assumptions about adversarial capabilities made by previous attacks. Assuming that only the adversary is capable of observing labels assigned by the model to inputs of its choice, they validated their attack design by targeting a remote DNN served by MetaMind, forcing it to misclassify 84.24% of the adversarial samples. Additionally, the paper discusses on how they conducted an extensive calibration of their algorithm and generalized it to other machine learning models by instantiating it against classifiers hosted by Amazon and Google, with a success rate of 96.19% and 88.94%. Next slide. So now for the substitute model and also for the attack we've used, which is spectrum simulation attack, we had to look into another paper which can be accessed through the link provided here. In this paper, I'll be going through summarize the contents of this paper. So white box attacks are highly effective but impractical in real-world scenarios. In contrast, black box attacks rely on cross-model transferability of adversarial examples, where adversarial examples are generated on a substitute model and then applied to a victim model. However, the transferability between models is often low due to the substantial differences between them. To address this issue, the paper introduces the concept of model augmentation, which aims to simulate divert models by applying transformation to inputs. Existing methods for model augmentation focus on the spatial domain, but this approach may overlook essential differences between models. To better capture these differences, the paper introduces the concept of spectrum saliency map, which represents the gradient of model loss function with respect to the frequency spectrum of the input image. Spectrum saliency maps vary significantly between models. indicating distinct interests in different frequency components. Motivated by this insight, the paper proposes a spectrum transformation technique based on discrete cosine transform, DCT, and inverse discrete cosine transform, IDCT, to diversify input images. The authors additionally prove that this transformation generates diverse spectrum saliency maps, simulating diverse substitute models. By averaging the results of diverse augmented models, the proposed spectrum saliency map effectively narrows the gap between the substitute and victim models. Next slide, please. So as you can see here, this is a snapshot from the paper. This figure visualizes the spectrum saliency maps, which is the average of all the images for normally trained models. And the snapshot B to C is the result of the scale invariant and admix transformation conducted in spatial domain, while image D to G is the spectrum saliency map of different models significantly varying from each other, which clearly reveals that each model has different interests in the same frequency component. Next slide, please. So now we look into the attack algorithm used in the paper. So the attack algorithm introduced in this research paper builds upon the proposed spectrum transformation method, which is designed to enhance the transferability of adversarial examples. The authors suggest that this transformation can be integrated with any gradient-based attack methods. Specifically, they propose a new attack algorithm called spectrum simulation iterative force gradient sign method. IFGSM stands for Iterative Force Gradient Sign Method, which is a common gradient-based attack. The spectrum simulation component refers to the application of the spectrum transformation to the attack process. Next slide. So as you can see here, we put a snapshot of the pseudocode for the attack algorithm. So basically, the proposed attack is divided into 3 steps. So from the snapshot, the first few lines 3 to 6, they applied their spectrum transformation to the input image so that the gradient is obtained from the substitute model, which is approximately equal to the result obtained from a new model, that is model augmentation. Then secondly, on line 7, we average the augmented model's gradient to obtain a more stable update direction. Finally, line 8, we update the adversarial example. Thank you. I shall now pass to my teammate, Chenshaw.
All right. Now I'm going to talk about the changes we made since we decided to use the Clever Hans black box attack paper. We decided to use a pre-trained PyTorch model that is converted from widely used TensorFlow models because there's a substitute model mentioned in the paper that substitutes for the DNN. And we chose momentum iterative method from the various attack methods in Clever Hans library. But then we faced a hard time trying to adapt MIM, which is momentum iterative method, to the current spectrum simulation attack, because we used the pre-trained model from the spectrum simulation attack paper, as the black box Clever Hans paper did not provide any code about the model, so we had to choose a model from another paper. And when we tried to adapt the MIM to the SSA model, it was not compatible. And with the time constraint, we decided to go with SSA because we've been doing the SSA model and we've been familiar with the SSA attack too. So we didn't have much time to implement huge change, but we did increase the batch size from 10 to 20. This would allow the process to be faster and increase the efficiency and all that. And this is the spectrum simulation attack, or SSA, that we were trying to replace with MIM, but then we just decided to go with this. And this was the final results after performing the SSA with increased batch size. You can see the result varies from 99.7 to 31%, but overall it was good. And here are some difficulties and the solutions we present to solve them. And the first was import error. This caused slow progress in the beginning, but fortunately this was fixed with the help of attending consultation with our tutor. And also the substitute model problem, because the Clever Hans Black Box attack paper did not provide any code about the model. So Professor Raphael suggested us to look into the spectrum simulation attack paper, and we decided to use the model for that. And then we found out the model was not compatible. And the teaching assistant told us this was common when we're trying something new. So due to time constraint, we decided to go with SSA instead of keep trying to implement MIM with the SSA model. So in conclusion, there's a lot of effort that is needed to implement the black box attack, because it doesn't just need a simple attack method, but also a suitable substitute model. And we certainly learned a lesson from that. And so we chose spectrum simulation attack. Uh, it's to boost the adversarial attacks from a frequency domain perspective. This is shown through a diverse spectrum saliency map. And testing on ImageNet dataset showed the method to be highly effective. It achieves an average success rate of 95.4% against various advanced defense models. This is mentioned in the SSA paper too. Now I'm going to share the full collab. So this is our Google Colab for the SSA attack. There's descriptions about what we're trying to do, about the black box attack, and of course SSA. And there are steps of how you're trying to do. And step one is preparing the model. So there are code about how you're gonna proceed with it. And step two is to prepare the attack method. We need the pre-trained models module for that. And step three is applying the attack. It mentions we change the batch size, and this code is to go to the SSA master module, and this code is to run it. And step four is to evaluate the attack success rate. Uh, oh, I forgot to mention this step takes a long time, like about 30 minutes. And verifying takes like around 1 or 2 minutes. It's the same structure as the attack. And in conclusion, we already said that in our slide. So yeah. So thank you for listening, and have a good day.